Okay, let's look at the second law of thermodynamics for open systems, and then we will also derive here the closed system as we've seen before. So in all its glory, this is the second law of thermodynamics, okay? Without any assumptions whatsoever for a control volume. You have a change in entropy over time for your control volume, and is going to equal to basically the entropy transfer as mass flows into and out of the system, as well as the entropy transfer due to heat interactions, because the only way for entropy to get in and out of a system, a closed system at least, is through heat, not through work. And in addition, you also have the rate of entropy generation within the control volume, which again occurs due to irreversibilities. So let's try to simplify this. So this we will not use dsdt. We will not use time variant in this entire relation. What we can do and say, let's see what happens when when a process is steady state. So when I have a steady state process, the dsdt goes to 0, like that. And so I get this. And so if I also say that I only have one inlet and one outlet, okay, I get that that the rate, the entropy change in time, the steady state entropy change in time, is just equal to the summation of all the entropy transfer due to heat transfer plus the that of the entropy generation. Okay, it's very similar to the closed system expression. If you go back and look at it, it's very similar. Okay, because we're imposing that there's no flow. Sorry, we're opposing that there's no time variation, and so it kind of looks like that. And so let's look at a closed system. So in a closed system, if this is the top here, the for relation, what I'm going to do is I'm going to remove the flow scenario, and I get that ds dt is equal to very similar, as you can see, to this idea. So basically, for a closed system, I replace this delta S with ds dt for the control volume. Sorry, for the control mass. This should say control mass, Cm, Cm. This is correct, Cm, Cm. So this is for the control mass for a closed system. Okay. Now we'll discuss steady flow assumption to try to get the flow work, the work due to flow for a system. All right. So if you look at the first law of thermodynamics, okay, and you can derive a relation for an adiabatic process whereby this occurs. This is basically sort of like a Bernoulli equation with work. And so what we're saying in this scenario, so I just kind of plucked it out of the first law of thermodynamics. What we're saying here, and especially is true if you remove the KE and the PE, which sometimes occurs, that you can have a workflow, okay, meaning the work due to a liquid or a gas flowing, say, a pipe or whatever in some region. You can either get work out of it or you have to apply work to it. So what the heck am I talking about? Let's say I have a turbine, okay, and I have some gas flowing through the turbine, okay. I can use the relation, top relation here, to see how much work I will get as the gas flows across the turbine blades, all right? I can also use the relation to determine how much work I need to push a liquid using a pump. So if I get a liquid from the bottom of a hill to the top of a hill, I can use this top relation, which is basically a Bernoulli, to see how much work is required to lift it, okay? And so it tells us a lot about the choice of material to use. Since liquids, so let's say we're ignoring the KE and the PE for a second, just so you could see something a little more quantitative with this idea. So I basically have work is equal to VDP, okay, negative VDP. So V is the specific volume. The specific volume for a liquid is low, the specific volume for a gas is comparatively higher. Okay, so if I have a gas, the work term is high. And if I have a liquid, the work term is low. So it works to my advantage and disadvantage depending what I want out of it. If I have to provide work, then I should use a liquid because the work will be low. If I have to get work, which like out of a turbine, then I should use a gas. Okay, so that's why we use liquids in pumps rather than like gases in a pump. We use a liquid in a pump, which explains why in all the cycles we've done so far, we try to remove any gases when we're trying to recover the original state into the turbine. So if you remember, out of the turbine comes a substance that's got both a liquid and a vapor at equilibrium, and then we compress it to get rid of all the vapor. The reason we're doing that is because it requires work, which costs a lot of money to move a gas. So we get rid of the gas. Now we have only a liquid. So we pump it through a liquid, and then it costs us a lot less. And so that's why we do that. Okay. And of course, if I have a turbine, I'm not going to put liquid water through it because it's not going to give me much. Okay. Now, I also want to kind of give you a connection. We discussed enthalpy in the past, and enthalpy is just the flow work. That's all it is. It's basically what we're just discussing on this page. Delta H is a way to measure how much work a liquid will give you or how much work a gas will give you. Okay. I'm putting an asterisk because it assumes adiabatic conditions. If it is not adiabatic, then delta H is work and heat together, sort of like the first law, just with delta H. But either way, the way we derive delta H, if you remember, I pulled originally, when we discussed the first law of thermodynamics open systems, I pulled a term out of work, okay, specifically, so that we get enthalpy rather than internal energy, because enthalpy gives us more information about the workflow, and it is very important in this idea. Okay, again, for a polytropic process, as I just showed you with the adiabatic process and the isentropic process, it's the same idea as before. A second ago, I showed you all of these relations with K. It was K minus 1 over K, and K minus 1 over here. That was for an adiabatic process. That occurs for an ideal gas when N is equal to Cp over Cv. When N is not equal to Cp over Cv, it is just a polytropic process, and you cannot assume the Q is 0. Okay? This is the work of expansion. We've discussed all of this. But if you're trying to get the flow work term for a polytropic process, meaning you're deliberately trying to understand, you know that a gas is expanding polytropically, you can get the work of expansion. If you know that a gas is flowing through a pipe, you're trying to understand the flow work out of that, or you're trying to understand how much work you have to put into it to make it move. Okay, then you use the bottom relation right over here, which is fairly similar to this one. We can derive this, and in fact, we will.